Oxidation and reduction reactions involve transfers of electrons. So we have to find a way of keeping track of the electrons being gained by the substance that is reduced and the electrons lost by the substance that's oxidized. And we do this using something called an oxidation number or an oxidation state. These are effectively a hypothetical charge given to atoms within a compound or a polyatomic ion. So this hypothetical charge is assigned by artificially dividing up the electrons among the atoms in the molecular ion. And we use a set of rules to assign oxidation numbers. The rules are given on the left-hand side of the screen. Elements in their elemental form have oxidation numbers of 0. The sum of the oxidation numbers in a polyatomic ion or molecular compound equals the charge on that species. And we have a couple of guidelines. Oxygens are generally -2. Halogens generally have a -1 oxidation number. Fluorines every time. And hydrogen typically has a +1 with nonmetals and a -1 with metals. So we'll give you some examples of how this actually works. The box at the bottom of the screen has a number of different example species. So we'll start with anything in its elemental form. So if you look at the box, chromium and sulfur are in their elemental forms. Chromium's natural elemental form is simply Cr. Sulfur naturally occurs as S8. In their elemental forms, the oxidation numbers for these things are always 0. Next, we'll use the second rule. The sum of the oxidation numbers equals the charge. So we'll look at something like Mg2+. Mg2+ consists of a single atom with 2 electrons removed, making the Mg2+ ion. The charge on that species is 2+. It is the only atom involved, so the oxidation number on that magnesium ion is simply the charge, 2+. So the oxidation number for any monatomic ion is simply the charge on that ion. So this would be true for something like N3- or Fe3+. The charges on those monatomic ions is the same as the oxidation number. Next, we'll look at a couple of polyatomic ions. Even though these are polyatomic and not monatomic, the oxidation numbers still add up to give you the charge on the overall species. So for SO3 2-, the oxidation numbers of the sulfur and all 3 oxygens have to add up to give you -2. So the oxidation number for oxygen is generally -2. There are a few exceptions, but we largely will not deal with them in this course. So what we can do is we can substitute that -2 into the ad hoc equation that we've built. So now we can say that the oxidation number for oxygen is -2. And there are 3 oxygens, each has an oxidation number of -2. And by solving our equation for sulfur, we can find that sulfur has an oxidation number of +4. A similar method can be applied for NH4+, the ammonium ion. We have to use the rules for hydrogen. When hydrogen is bonded to a nonmetal, it has a +1 oxidation number. So now we know hydrogen's oxidation number is +1, and by solving our equation, we can find nitrogen's oxidation number, in this case, -3. Our third example is the hydroxide ion, OH-. The same method applies. In this case, we already could guess what our oxidation numbers are. Oxygen is typically -2, and hydrogen, when bonded to a nonmetal, is +1. And conveniently, when you add those 2 numbers together, you're left with the charge on the overall structure, which is -1. Next up, we'll look at just a few of the remaining examples, starting with lithium hydride. Lithium hydride contains a metal ion bonded to an H ion. And when hydrogen is bonded to nonmetals, it ends up with a -1 oxidation number. And the overall charge on this structure is 0. Lithium hydride is neutral, so our charge is 0. So lithium's oxidation number plus the -1 from the hydrogen equals 0, which means lithium has to have an oxidation number of +1. If you look at AlF3, again, the overall charge is 0. Fluorine is a halogen. It always has a -1 oxidation number. Some of the other halogens can have different oxidation numbers, but fluorine always, every time, will have a -1. And this means that aluminum must have a +3 oxidation number. Of the remaining 4 options, we'll only do sodium carbonate, and I'll leave the other ones for you to practice. Based on the rules that we've given here, it might not be completely obvious how to figure out the oxidation numbers for all of these atoms. If you look at the rules on the left-hand side, the only one that obviously applies is oxygen having an oxidation number of -2. We don't have any rules regarding carbon or sodium. But what we can do is we can remember that the sum of the oxidation numbers equals the charge. And this is true for neutral species, and it's true for ions. Sodium carbonate is an ionic structure, so it's really composed of sodium ions and carbonate ions. There are 2 sodium ions, but they're exactly the same as one another. They have an Na+ structure. There's only 1 carbonate ion. It is a CO3 2- ion. So what we can do is we can work out the oxidation numbers for the ions, and they will be the same oxidation numbers that are present in the ionic compound. Sodium is easy. The sum of the oxidation numbers equal the charge. There's only one thing involved, and the charge is +1. Therefore, the oxidation number is also +1. The carbonate ion is slightly more complicated, but it's exactly the same as examples we've done before. Carbon's oxidation number plus 3 times oxygen's oxidation number equals -2, the charge on that structure. This indicates that carbon has a +4 oxidation number.